Okay, today we'll move on to the next problem on HGL and TEL. So our question is, a horizontal pipeline 40-meter long is connected to a water tank at one end and discharges freely into the atmosphere at the other end. For the first 25-meter of its length from the tank, the pipe is 15 centimeter diameter and its diameter is suddenly enlarged to 30 centimeter. The height of water level in the tank is 8 meter above the center of the pipe. Considering all losses of head which occurs, determine the rate of flow. Take F is equal to 0.01 for both sections of the pipe. Draw HGL and TEL. So we have to draw the figure. So this is that figure. There is a tank. Connected to that there is a pipeline going. But it said that for the first 25 meter of its length, it is having 15 centimeter diameter and then it's doubled to 30 centimeter diameter. So you have to draw accordingly. Okay. First one will be having a smaller diameter than the second one and mark its lengths, that is 25 and 15, and total it is 40 meters. Okay. And next they have said that from the center line of the pipe in the tank there is a free water surface is up to 8 meters from the center line of the pipe. So you have to mark that also. Now I've converted everything into meters. I've marked L, L1, L2 and head in the tank, and D1 in meters and D2 in meters. Now they have asked to draw the GL and TL. Also they have asked the discharge. So none of the velocities are given. So what do we need to do? First of all, we need to apply the Bernoulli's equation. Okay, as usual, as in the previous case, we need to apply the Bernoulli's equation at 2 points. That is at the free surface of the water in the tank and at the exit of the pipe. Okay. So why? So that we will get a very minimum equation with minimum terms. At the free surface of the tank, we know that it is atmospheric pressure is 0, and at this point also atmospheric pressure is 0. So we need not find the pressure head. Okay. And then at the free surface of the tank, we know that the velocity of flow is very much less compared at this point. So we can neglect this also. So only V2 will be there. So unlike the previous question, what I have marked is the V1 as the velocity of flow in the first pipeline and V2 as the velocity of flow in the second pipeline. I did not mark any velocities here. Okay, I am taking it as V. Okay, now apply the Bernoulli's equation to the free surface of water and at the outlet of the pipe. So now we will get the equation. I did not give any 1 or 2 notations here. So it is P by rho G plus V square by 2G plus Z. That is at this point. Okay. Is equal to, at this point we know it is P2 by rho G plus V2 square by 2G plus Z2 plus all losses, since they have asked us to consider all losses. Okay, now at the free surface of water at this tank, we know that it is pressure head will be 0. Why? Because it is atmospheric pressure and it is open to atmosphere, and we know that atmospheric pressure is taken as 0. Therefore, this term becomes 0, and we know that at this point at the free surface, velocity of flow will be very, very less, isn't it? The area is very much large compared to this. Obviously, but the discharge will be the same in both. So, obviously, the velocity will be very, very less, and we can take it as 0. So, I am also taking the velocity as 0, and only the datum head remains, right? So, from the center line of the pipe up to the free surface, they have already said that it is 8 meter. So, it will be 8 meter. Datum head will be 8 meter. And at the exit of the pipe, the pressure head is 0 again. Why? Because it is open to atmosphere. It is being freely discharged into the atmosphere. So, P2 by rho G is 0. V2 is there. So, that term is there. V2 square by 2G is 0. Sorry, is not 0. That term will be there. And the datum head will be again 0 because this datum line is passing through the center line of the pipe, isn't it? So, the datum will be 0. There is nothing to take. And we know that there will be major losses and the minor losses. So, here the major losses are frictional losses through the pipe. When the water is flowing through the pipe, there will be major losses. So, first pipe there will be HF1, second pipe there will be HF2. So, that's what I've marked here. And then what are the minor losses experienced? As in the previous case, we can see that from the tank there is an inlet, right, to this pipe. So there is an inlet loss, minor loss happening at the inlet of the pipe. So we have to consider that. And this point also, this is also the exit of first the pipe and the inlet of the second pipe. And also there is a sudden enlargement also happening. Okay. Now comparing both of these, that is exit of the pipe loss and the sudden enlargement loss, the losses due to the enlargement is more, that is V1 minus V2 the whole square by 2g, that is the loss due to sudden enlargement. It is more compared to the exit of pipe loss. Okay, so you need to take only one of the losses. Do not take both. Okay, whichever is greater, take that. So that's why I am taking the loss due to sudden enlargement. Do not take any losses here. This is freely discharging into the atmosphere. We need not need to consider any losses at the end point. Okay, so there will be two losses, inlet of pipe loss and the HE, which is due to the sudden enlargement of pipe. Okay, now marking all of this in our previous equation, it is A is equal to B2 square by 2g plus 4 FL1 V1 square by 2g D1 plus 4 FL2 V2 square by 2g D2 plus 0.5 V1 square by 2g plus V1 minus V2 the whole square by 2g. These are the equation for the minor losses. Okay. Now this equation is in terms of two unknowns, isn't it? V1 and V2 is unknown. So we cannot solve both of that V1 and V2 with this equation alone. So what do we need to do? At least we have to write V1 in terms of V2 or V2 in terms of V1. So how can we do that? We have got one more equation, right? That is the continuity equation. So apply the continuity equation. We know that in both of those pipes, the discharge will be same, isn't it? So A1 V1 is equal to A2 V2. We can equate both, and by writing this V1 is equal to A2 V2 by A1 and substituting the values itself, we'll get something like V1 is equal to 4 times V2. Okay, what I've done here is I've taken D2 as 2 times D1, which is the case, right? See, this is 15 and this is 30 centimeter. So actually the diameter have been doubled here. So we can take it like that. So we'll get V1 in terms of V2 like this. V1 is equal to 4 V2. Now substitute everything back into the first equation and write everything. Back in this first equation, we have to substitute everything back and write everything in terms of V1 or V2. Okay. Now I've written everything in terms of V2, isn't it? Okay, so 8 is equal to V2 square by 2g plus 4FL1 V1 square was there. So we have to substitute 4V2 here and you have to take the whole square. Okay, at these points I've seen that many are making calculation mistakes. You have to square the whole thing. Okay, now we'll get, and finally solving this equation. Now this equation is, everything is in terms of V2 itself. Okay, V1, wherever V1 is there, we have substituted in terms of V2. Now solving this equation, we'll get V2 as 1.113 meter per second. Now we know that they have asked for the discharge, isn't it? So discharge is A1 V1 is equal to A2 V2. Either you can substitute in both of these equation or either one. So we'll substitute in the A2 V2 because we have already found out V2, right? So Q is equal to A2 V2. Substituting for the values, we'll get discharge as 0.07867 meter cube per second. If we want it in liters per second, you can express it like that. Now, the next question is to express the total energy line. That is to draw the total energy line. So how to draw the total energy line? And going back to the figure, we'll be taking this point, that is at the free surface, inlet, and this point and at the exit. Okay, so first one is the free surface of water. At the free surface of water, we know what is total energy, that is P by rho g plus V square by 2g plus Z, isn't it? So at this point, P by rho g and V square by 2g is 0, only Z remains and Z is 8. So at the free surface of water, total energy is 8 meter. Now draw another figure and mark this 8 meters, okay, and mark the point as A. So this is how our total energy line starts. Okay, and next is the inlet of the pipe 1, that is losses that is this point. This is the inlet of the pipe. There is losses, that is a minor loss due to the inlet of pipe. Therefore energy will decrease. Okay, the total energy will decrease. So you'll have to subtract the losses from the total energy we have obtained at the point A. That is, you have to subtract 0.5 V1 square by 2G from 8. Okay, now substituting the values for V1 and getting the losses as 0.5 meter, the total energy at the inlet of the first pipe will be 8 minus 0.5. That is, there is a drop of total energy. Okay, now we have to mark that also. Here I have marked as from the center line, it is 7.5. So there is a small drop of 0.5. So this much is the loss. Okay, 0.5 is the loss. And mark it as B. This will come in at the inlet of the pipe, isn't it, at this point. And next is at the exit of the first pipe. We know that at the exit of the first pipe there is major frictional loss happening, isn't it? Therefore, HF1 is equal to 4F1 L1 V1 square by 2GD. Substituting everything, we get the HF1 or the major frictional loss as 6.73. So by the time the fluid has been flowing from this inlet to this exit of the first pipe, this much of head is being lost. 6.73 meters has been lost due to the friction. So you need to mark that also. So we need to subtract that first, isn't it? So up to the inlet, that is up to this point, we get the total energy as how much? 7.5, isn't it? Up to this inlet it was 7.5. From that, this much of loss is happening when we have traveled from the inlet of this pipe to the exit of this pipe. Okay, so we have to subtract that loss. Therefore, it is the total energy at the exit of the first pipe is 7.5 minus 6.73, which is equal to 0.77 meter. Okay, now we have to mark that also. That is, we have reached till here, right? That is the point B. It was 7.5. Now minus 6.73. What will we get? How much is that? 0.77 meter. So this is that 0.77 meter. This is that 0.77 meter. That is at the point C. There is a significant drop in total energy. That is why I have drawn a slanting line. That is, this much of frictional loss is there. I didn't mark the losses. Okay, I have just marked the total energy is happening. So at this point, from the center line of the pipe, the energy will be 0.77 meter. I'm sorry for this line. This is wrong. I've marked it wrong. So just don't concentrate on this line. Just concentrate on this. This is our HGL. Okay. Okay. So up to the point C, it is 0.77 meter. Now, at the end of the first pipe, or at the exit of the first pipe itself, there is a sudden enlargement loss also, isn't it? That is, at this point, at the end of this point or end of this pipe, it is suddenly enlarging, or that is, its diameter is being doubled. So there is a sudden enlargement of the pipe. Therefore, there will be losses, that is due to the sudden enlargement, minor loss due to sudden enlargement. So we need to find out that loss also. That is, when we substitute all these values, we'll get it as 0.568 meter. And total energy at the exit of the pipe again drops from 0.77 meter to 0.202 meter. That is, we have to subtract this 0.568 from 0.77 meter. And we'll get the total energy at the exit of the first pipe as 0.202 meter. Okay. I've marked it here. I hope it's clear. That is, at the exit of the pipeline, see, there's a small drop from C to D at this point itself. And we get finally this much as the total energy at that point, which is 0.202. Okay. And then what happens is that again the pipe is traveling. At the exit of the pipe 2, there is again major frictional loss, HF2. When we substitute all the values, we'll get it as 0.126 meter. Okay. Therefore, the total energy at the exit of the pipe 2 will be how much? This was the total energy at the exit of the first pipe, right? So after traveling from the first pipe to the second pipe, again there is frictional loss. So up to this point it was how much? 0.202. So we have to subtract this frictional loss from 0.202. That is 0.202 minus 0.126. We'll get it as 0.076 meter. That is the total energy at the exit of the pipe 2. See, the only energy left is only 0.076 meter at the exit of the pipe 2, and I've marked it as E. So this is our total energy line. That is A, B, C, D, E is our total energy line. Okay. So we have drawn the total energy line. And next is how to draw the hydraulic gradient line. Okay, how to draw the hydraulic gradient line? Hydraulic gradient line is nothing but pressure head plus datum head. Also we can find it out by, we know the total energy at some point. If we subtract the velocity head at that point, we'll get the hydraulic gradient line. Okay, now at the point A, what's happening? We know the hydraulic gradient as P by rho g plus Z, that is 0 plus 8, which is equal to 8 meters. So it starts from the point A itself. Okay, I've also drawn it through the green color. I hope it's clear. Okay, and at the inlet of the pipe that is at this point, we know that the total energy, we'll get the hydraulic gradient by subtracting the velocity head from the total energy at that point. So the total energy at the inlet of the pipe was how much? We have marked it here, right? The total energy at the inlet of the pipe after considering all the losses was 7.5. From this we need to subtract the velocity head. We know the velocity head, we know the v1, so v1 square by 2g, just subtract it, we'll get it as 6.5. So mark 6.5 from the center line of the pipe at the inlet of this first pipe, mark it as the point G. So it is AG. Okay, there's a drop from A to G. Okay, that is our hydraulic gradient line, second point. And the rest we don't have to compute everything like this at each point. The rest is like we have to draw the total and hydraulic gradient line always parallel to the total energy line. Just draw parallel lines to the total energy line. Okay, so I've drawn a parallel, and again there is a parallel line going like this, and at the end point, that is at the point F, we know that the hydraulic gradient line will be how much at point F? This is the exit of the pipe, right? P by rho g plus Z at this point will be how much? This is also open to the atmosphere, and the datum line is the center of the pipe itself. So both of these terms will be 0 and it will be equal to 0. So just you have to mark it at the center line of the pipe itself. So this is our hydraulic gradient line. Okay, just draw parallel lines to the total energy line. Okay, join this, and the AGHIF is the AGHIF will be our hydraulic gradient line. Okay, I hope this is clear. AGHIF is our hydraulic gradient line. Okay, so now we have solved two problems in hydraulic gradient line and total energy line. Okay.